Bitaw ng mahinahon ako ba'y lulubayan ng ating mga kahapon na di na kayang ayusin ng lambing.
A pleasant day to each and everyone. My name is John Kelvin Magbohos, and we are here to present to you our final project, which are fuels and lubricants. Our group is composed of Bayanito, Maria Cristina, and Daya Lawrence, Magbohos John Kelvin, Raven Recon, Saldana Leo Angelo, and Salud Carl Jan Christian. In our table of contents, there are seven topics that we will tackle about. First is the theory, second is the objectives, third are the materials and reagents, fourth one is the procedures, fifth is the observation and calculations, sixth is the self-evaluation, and lastly are the safety reminders. So we are gonna start first in theory.
Good everyone, I'm Lawrence Amendaya and I'm here to discuss all about the theories behind the experiment that we chose. So before understanding what laminar diffusion flame is, we must first determine what components are needed in order to produce these flames. So to know that, we must first understand what is combustion, what's the combustion process, and the different components that are needed to create specific fires. So basically, combustion is defined as a chemical change process wherein different oxidizing agents such as oxygen, ozone are needed, and it is infused with different types of fuels as well as a heat source to produce the fire. And those are the three components needed to produce the flames. So basically, the first one would be the fuels, and the fuels have different types such as biofuels, diesel, kerosene. Those types of fuels are some of the components that are needed to create fire. And as well as the oxidizing agents, there are different oxidizing agents present, wherein these agents enable the transfer of protons. So basically, some of these are oxygen, hydrogen peroxide, nitric acid, and ozone. So the main topic of our experiment would be the diffusion flames. And through this diffusion flames, we are discussing the interaction between the fuel and the oxidizing agent to create the specific fire that we need. And through this fire, we're going to test the parameters wherein we're going to conduct different calculations to know the relationship between the height, the flame height, the time elapsed to create the specific height, and the volumetric flow of the fuel produced.
This laboratory experiment aims to understand the jet diffusion flame, understand the concept of laminar jet diffusion flame height, derive a relation between laminar jet diffusion flame height and rate through phenomenological analysis, observe the effect of volumetric fuel flow rate on laminar jet diffusion flame height through the experimentation, and to compare the results with Roper's empirical formula. For the materials we used, CNG, or compressed natural gas tank, needle valve, pipes, rotameter, Bunsen burner, digital camera, and tripod, which is only optional. These materials are needed to be prepared beforehand and in good conditions to prevent unexpected circumstances while doing the experiment.
Next is the procedure. As we can see at the picture, we have the CNG or the compressed natural gas attached with a needle valve, and the rotameter then attach it in a Bunsen burner, and the flame which is ignited by the Bunsen burner, and a digital camera with a tripod. So the first step on conducting this experiment is to first, the camera has to be positioned at a distance where the flame of maximum height is captured. Then second, make sure the CNG fuel or the compressed natural gas fuel is set to the desired flow rate using calibrated rotameter and ignited at the tube exit. Then the third one, video the flame should be taken for a certain time. Then repeat the procedures for different fuel flow rates to determine the difference between them. And lastly, the time period of video for each flame should be kept constant in order to extract equal number of frames from the videos.
Now we're heading to the observations and computations of our experiment. First, we set some parameters about the CNG or the compressed natural gas, which are density, the diameter of the burner, and the set increments for the volumetric flow rate or the fuel. The first one is the density. Density of our fuel is, based on our research, is around 180 kilograms per cubic meters. And then the set diameter of the burner that the group chose is 2 millimeters, which gives us a radius of 1 millimeter. And then the next one is the increments for the volumetric flow rate. Our increments is 0.2, starting from 0.2 cubic meters per second. And then, as you can see here in the table, we have already tabulated the data from our experiment. The darker shade of blue represents the height of the flame, which is determined by using the conventional computation, and the lighter shade of blue shows the results from the experiment using the Roper's empirical formula. And then next slide, we can see the summary of the data data from gathered from the experiment. The left side showing the conventional computation, and the right side shows the Roper's empirical formula. And then, as you can see here, there is a formula which states that in the conventional computation, it states that the height of the flame is equals to the density of the fuel all over 2 pi times the density of the fuel times the diameter of the burner, whereas the Roper's empirical formula denotes the height of the flame, which is equal to 1,300 times the T sub O, which means the temperature of the surroundings, then all over T sub F, which means temperature at which diffusivity in the gasoline starts, and it is said to be, or it is determined to be 1,500 Kelvin, times the natural logarithm of 1 plus quantity 1 over S, and the S denotes the ratio of air to fuel volume, wherein complete combustion happens. Then times, and all of that is raised to -1, so it becomes the denominator of the equation times the Q sub F, or the volumetric flow rate of the fuel, or the fuel. The volumetric flow rate is also provided the height of the flame, so those are very important. That's why we made it in increments of 0.22 to determine some patterns, some distinguishable difference between using the conventional computation formula and the Roper's empirical formula.
For the self-evaluation of this experiment, our group measured the flame height of a jet diffusion flame. Shown in the result at figure 1, we concluded that the flame height or the flame length is directly proportional to the volumetric flow rate of the burner. This indicates that the visible height of laminar jet flame or jet diffusion flame increases with the fuel flow rate. In addition, considering the phenomenological considerations, it is shown that the visible flame height of a laminar jet diffusion flame is found to be increasing linearly with the fuel flow rate. Additionally, the analytical model of Roper's, or also called as the Roper's analysis, for stoichiometric flame length predictions was found to hold for normal and inverse diffusion flames over a wide range of conditions. These predictions of visible flame heights from Roper's analysis indicates that the flame heights are generally smaller than the experimental data due to the assumed flame length or the temperature of the flame, or the TF. From this experiment, we also concluded that the Roper's formula is proposed to improve generality and accuracy. Thus, the Roper's analysis is proposed or more likely to give more accurate predictions of flame height in accordance with the phenomenological analysis, especially at a lower fuel flow rates. Thank you.
Our safety reminder is composed of conducting experiment on a ventilated room, turning on exhaust fans before conducting the experiment, performing a leak test, initial flow rate must be kept at a minimal level, the fuel supply must be stopped on occasions of failure at igniting fuel multiple times, and lastly, always keeping a fire extinguisher nearby. Listed here are some of the references of our final project. And that concludes our presentation. Thank you.